All right, Chemistry 3111. Can everybody see my slides? My students who are here, my wonderful, wonderful students. All right, thanks a million, Courtney. I appreciate that. Anybody who signs up for Chemistry 3111 is a wonderful person, right? All right, well, let's get started here. In last class, we finished off by talking about amino acid synthesis, so we spent some time on that. And now we want to turn our attention to the structure of peptides. And we talked about how last class we said if you have a few amino acid residues or a few amino acids linked together, we call that a peptide. And only once you get up to, over 50 or something, then we call it a protein. And here's an example of a tripeptide, right? Tripeptide means we have 3 amino acids linked together. And again, sometimes we call those residues. So we would say 3 amino acid residues linked together. Glutathione, we abbreviate this tripeptide as GSH. So sometimes biochemists might talk about a GSH adduct, and that just means that the glutathione reacts with another molecule. Anyhow, you can see that glutathione is made from 3 amino acids. It's made from glutamic acid, it's made from cysteine, and it's made from glycine. And you see they even have the words residue there, the glutamic acid residue, the cysteine residue, and the glycine residue. But the thing is, it's not just enough to take those 3 amino acids and throw them all together and make new bonds and you end up with glutathione. No, they have to be bound in that particular order. You have to have the glutamic acid bound directly to the cysteine in the middle, and then you have to have the glycine bound last in the way that it's drawn here. And you see that the carbonyl of the carboxyl of glutamic acid is bound to the nitrogen of the cysteine, and you see that the carbonyl of the cysteine is bound to the nitrogen of glycine, like that. You also see that I'm using the 3-letter abbreviations here, GLU, CYS, and GLY, which you don't have to have memorized in this class. There's also the 1-letter abbreviations, which would be E, C, and G, like that. Again, you don't have to memorize those. But again, if you're somebody who might be biochemistry minded, it would be a good idea to have these structures, 3-letter and 1-letter abbreviations memorized, because you will need to know them for a 3000 or a 4000 level biochemistry class. Anyhow, what I'm saying is this: if this is the correct sequence of the amino acids, okay, if you were to just mix them like this, if you were to do this, or if you had, this, okay, these would not be glutathione. So these would not be glutathione. And again, the reason why glutathione is an important molecule, I failed to mention that, is because it's a scavenger of radicals in the body, and it also reacts with different electrophiles in the body, because you have the thiol here, which can be a really good nucleophile, so it can act as a nucleophile. Anyhow, that's neither here nor there, but the idea is that the tripeptide has to have the amino acids linked in a specific order in order to make this molecule glutathione. Well, what about a dipeptide? Okay, let's make it a little bit simpler. Let's say we had alanine and glycine, 2 of the simplest amino acids, right? The R group of alanine is just a methyl group. So the R is nothing more than a methyl. Whereas on glycine, the R group is just a hydrogen, right? So these are probably the 2 simplest. Well, glycine is definitely the simplest amino acid. It has no chiral center. But if we were to create a peptide bond, which is just an amide bond between alanine and glycine, you see that there's 2 ways that we could link them together. We could either react the carboxyl of alanine with the amine of glycine to make this molecule, or we could react the carboxyl of glycine with the amine of alanine to make this molecule. And these 2 molecules, these 2 dipeptides, are not identical. Okay? These are 2 different peptides, dipeptides. And so, if you wanted to only make one of them, let's say you only wanted them linked in this order. You wanted to have the alanine on the left and the glycine on the right, the way that it's drawn here. Well, we'd have to come up with a way to do that. And that's part of what we're going to talk about today. Now, something that you notice in both of these structures is that they both kind of are set up in the same way, that you have a nitrogen in both of them on the far left-hand side, okay? And we call that the N-terminus. And they both have a carboxyl on the far right-hand side, and the carbon of the carboxyl, we call that the C-terminus. So the N-terminus and the C terminus. And if you're wondering why I said terminal, it's because sometimes people call it the N terminal and the C terminal. So let me show you over here. It says peptides have an N terminus and a C terminus. It's a convention for biochemists. It's a convention for organic chemists. It's a convention for biologists, for everybody to write the N terminus on the left-hand side of the molecule, and we always put the C terminus on the right-hand side of the molecule. It's always done that way. So when you're writing out a peptide, okay, whether it's a dipeptide, tripeptide, so on and so forth, depending on the number of amino acid residues you have, you just want to remember this, that you have that you have nitrogen, carbon, carbon, NCC. They always come in that order, right? You have the N terminus, the alpha carbon, and the carbonyl carbon. Then you have the N terminus, the alpha carbon, and the carbonyl carbon. You have the N terminus, the alpha carbon, and the carbonyl carbon, so on and so forth. Now this would make a tripeptide, but we go NCC, 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 and the second carbon is the one that always has the carbonyl on it. And we're going to get some practice in drawing peptides today. Okay. Now again, we can use the three-letter abbreviations. If you're wondering, why do these three-letter abbreviations even exist? Well, let's think about it. If you could say alanine, glycine, cysteine, tryptophan, gluten, right? If you list off all those amino acids, it's a lot longer than if you just have these handy-dandy three-letter abbreviations, and a scientist or a student can just look at those and say, well, I know what those mean. I know that this is a leucine, right? Okay, no problem. I know this is a phenylalanine, what have you. And the one-letter abbreviations are even faster. But again, the convention is, and I'm repeating myself here, but I want to make sure you understand this, that we always have the N terminus on the left-hand side, and we always end with a C terminus on the right-hand side, and they always follow this order, right? NC carbonyl, NC carbonyl, NC carbonyl. And again, we're going to get some practice in writing out some peptides today. Now, a little bit more about the structure of peptides. And this goes, are you ready for it? All the way back to chapter 1 of Organic Chemistry 1. I bet you didn't see that coming, okay? You weren't like, boy, I bet you today in the second to last chapter in Organic Chemistry 2, I doubt he's going to bring up chapter 1, right? Well, I am, because you remember that in that chapter, we spent some time talking about hybridization. And we said, what's the hybridization of this nitrogen in an amide? It was a very specific example that we looked at. And the way that it appears when we look at the structure, the one that I have the blue arrow drawn to, it appears as if that nitrogen is just your regular old run-of-the-mill sp3 hybridized nitrogen. However, we know it's not, right? We know it's not because of these resonance contributors that are drawn here, right? In particularly this one where everything has a complete octet. Okay, the carbon has a complete octet. It doesn't right here, does it? But in this last structure, everything's got a complete octet, but there's a double bond to the nitrogen. That suggests that the carbon-nitrogen bond has partial double bond character. And what would be the result of that? It will have restricted rotation. Now, if that bond that I have the green circle around has restricted rotation, that's going to have some interesting consequences in terms of the shape or the conformation of a peptide or a protein or an enzyme. So let's take a look here. It says, as a result of the partial double bond character of that carbon-nitrogen bond of our amide, and there's lots of amide bonds in peptides, aren't there? Well, as a result of that partial double bond character, we have that restricted rotation, and that bond can either exist in what's called an S-trans or an S-cis conformation. It says here rotamer, okay? Now, if you're wondering about the S-cis and the S-trans, the S just stands for sigma, okay? Because at the end of the day, this is still drawn as a sigma bond, isn't it, right? This is a sigma bond, this is a sigma bond. And we don't think of sigma bonds as having trans and cis. But if there is that partial double bond character here and here, which again causes the restricted rotation, we can think of a trans and cis, right? And most of the most of the peptide bonds are going to have the groups trans to each other, right? Because there's less steric hindrance than if they're in the S-cis conformer, okay? And the barrier of rotation is pretty high. It's 80 kilojoules per mole. Now, if you've spent any time studying the structure of peptides and proteins, you've probably heard of this before, or you maybe weren't aware of this, but you probably understood that, proteins do have some conformational restriction. However, because not all of the bonds in the peptide or the protein possess this partial double bond character, they can adopt some very interesting conformations. So let's take a look here. It says peptide bonds of the peptide backbone have the preference for the S-trans conformation. So if you look at each one of the residues, here's a residue from an amino acid, right? Here's another one here, okay? So on and so forth. But you see that the bonds that are highlighted in green, those are the only ones that experience that restricted rotation. That means that this bond, this bond, this bond, this bond, this bond, right? All those bonds have free rotation, don't they? Right? They all have free rotation. And again, because those bonds have free rotation, a peptide or a protein or an enzyme can adopt a number of conformations, right? And if you've ever studied the induced fit model and the lock and key model, you've probably talked about the conformational mobility of enzymes and proteins. But anyhow, that's for another day. All right. So something else that's interesting about the structure of peptides is based off of this amino acid, the cysteine. Okay. These are cysteine residues here. So this is cysteine. Okay. And this is cysteine. Okay. I'm saying that as carefully as I can because I want to emphasize that letter E in there in the cysteine amino acid. Well, cysteine residues or cysteine amino acids in a protein can connect through a disulfide bridge, and they actually make a molecule. The molecule that's shown here, this is called cysteine. Okay, cysteine. Now, how do we know that this is oxidation? Well, if you remember, back in the day when we talked about oxidation and reduction, I told you there's a very simple way to view oxidation in organic chemistry, and that oxidation is the loss of hydrogens or the gain of oxygens. But here we're losing these two hydrogens, so that is oxidation. So in fact, if you've ever had a perm before, okay, I'm looking in your direction, Skylar. So if you've ever had a perm before, or if you've ever bought a home perm kit, this is essentially what you're doing is you break the disulfide bonds in your hair, and then you wrap them around a curler, and then you reoxidize them, and then anyhow, it's kind of interesting chemistry there if anybody wants to look into that. But that's how a perm works. But anyhow, the whole idea is that the oxidation that occurs when two cysteine residues combine to form this disulfide bridge is that it can have profound effects on the conformation of a protein. Okay, it has very profound effects. If you take a look at these two peptides here, it says the linkages, and these are the disulfide bonds. There's one shown here and the other one shown here. They have a great effect on the three-dimensional structure of a protein or a peptide, and of course they can affect the function, right? So we can have two types of disulfide bridges in a protein. We can either have an intrastrand that's inside the same chain. Okay, so that's intra, and if it's inter, just like international is between two countries, so between two different strands of a peptide or a protein. Anyhow, so you have to know what a disulfide bridge is, that it can greatly affect the three-dimensional structure and function of a protein, and we can have an intrastrand disulfide bridge and an interstrand disulfide bridge. Well, the next section is kind of an FYI in a way, or at least it's what it's always felt like to me. There's just some biologically relevant peptides that he presents in the textbook. And I mean, of course, there are many that aren't mentioned in our textbook, but I think the main take-home message is just how small changes in a peptide can have huge differences in terms of the function of a peptide. If you take a look at these two enkephalins here, we have leucine enkephalin. So the leucine enkephalin has a leucine on the C-terminus, and then we have methionine enkephalin. I don't know why I didn't highlight methionine, but anyhow, I didn't. So methionine enkephalin has a methionine on the C-terminus, okay? And they both function to control pain, but you do see that all they have is this one difference in their in the peptide structure, right? There's just one amino acid that's different between the two of them. Anyhow, so those are both pentapeptides. Bradykinin is another one. It's a hormone that dilates blood vessels, and you can see that it's a non-peptide. And again, I just think that he's really trying to drive home the point that these molecules, these pentapeptides, the two enkephalins, and bradykinin, the nonapeptide, they both have a very specific order in which the amino acid residues are linked together. And if you change that, well, you end up with something completely different. Some other examples that are shown over here are vasopressin and oxytocin, not OxyContin. That's like an analog of morphine. That's something completely different. But anyhow, vasopressin, you can see that it causes reabsorption of water by the kidneys and controls blood pressure. Now, something that you notice about vasopressin is that it's got a disulfide bridge in the molecule. And this is the N terminus over here where the cysteine is. But the glycine here, you see that it says NH2. What that means is that glycine would normally end like this, right? It would end with the C terminus being a carboxyl. But since they've gone deliberately and written NH2, that means that it's actually a primary amide like that on the end. And the same thing for oxytocin, which induces labor and stimulates milk production. So this is kind of what I was getting at, that these two molecules have very similar structures, but the only differences are the residues that are highlighted in red. Here you replace the phenylalanine, where's my green highlight? The phenylalanine for an isoleucine here, and then you swap out this arginine for a leucine here, and you end up with two different compounds that have very different effects in the human body, if you will. So again, a small change in amino acid residues can have profound effects. And of course, that's important when we're talking about illnesses too. Different genetic defects can result from what? Just the change in one residue in a protein in a person's body. So anyhow, that's not really the task at hand, but let's talk about drawing the structure of a peptide. Now, there's a couple of ways that we can do this. And if you go into our book, and I don't really have it in the right spot here, but I want to tell you that there is a skill builder. It's skill builder 25.3. So let me just scribble that down here. Let's see, how do you spell skill builder? Well, it's all one word, isn't it, right? Anyhow, so skill builder 25.3. If you don't follow me on this, we're going to take a look at now. This might be really helpful. Let me show you one thing very quickly, though. Okay, I'm going to show you two ways to do this. Okay, now all of you are Organic Chemistry 2 students. You've made it to pretty much the end of Organic Chemistry 2. You're pretty seasoned veterans at this point. You know a lot about organic chemistry. You spent a lot of time studying it. But I want to show you quickly, when I teach nursing level chemistry, so that's organic chemistry where they cover everything in like basically 2/3 of a semester, all the reactions that we cover. So there's no mechanisms or anything like that. It's not nearly as complex as what we look at, but I would teach them how to draw a tripeptide like this. Let me show you the way I would show them, and then I'm going to show you the way that I want you to do it, okay? So quickly, we have 3 residues. So what we're going to do is we're going to write N-C-carbonyl, N-C-carbonyl, and then we're going to write N-C-carbonyl again. This is the way I would teach it if I was teaching nursing chemistry, okay? The end is going to be a carboxylate, the C terminus, and the N terminus we're going to draw as the protonated form because we're going to say it's at physiological pH, okay? So now all I have to do, I know that the carbons that are in between the nitrogen and the carbonyl, these are the alpha carbons, right? These are the ones with the R groups. So now I'm going to put in the R groups for all 3 of these amino acid residues. So I know that for a leucine, it's a isobutyl group. So I'm going to put an isobutyl group. I'm going to kind of use a partially bond line structure here. So I'm going to put my isobutyl. Now this carbon needs a hydrogen. So I'm going to put the hydrogen in there. Okay, let's move on to the next carbon, okay? Alanine is just a methyl group. So I'll put a methyl group like this. So that carbon needs a hydrogen too. And then lastly, we have glycine. Well, the carbon on glycine has no R group, so it's going to need 2 hydrogens like that. So now the only thing it's missing is this hydrogen, or sorry, this nitrogen and this nitrogen. Those both need hydrogens attached to them because nitrogen has to have 3 bonds in a lone pair. So we'll put the hydrogens here like that. You can even throw in the lone pairs if you want. But now we've done it. We've drawn the tripeptide. So again, this should be the nursing level chemistry way of doing it. The way I want you to do it is this, okay? Because this is not nursing level. This is chemistry 3111. So we're going to start with nitrogen. We're going to draw it more properly, okay? So you have NC-carbonyl, and we have NC-carbonyl, And we're going to draw it as a zigzag because that would be more correct. So NC carbonyl, like that. Okay? So let's take a look. I'm going to move it over a little bit. Okay, I'll kind of move it over here like this. All right. So on our C terminus, we're going to draw it as a carboxylate. On our N terminus, we'll draw it as the protonated form. So on the first alpha carbon, we're going to draw the isobutyl group. So isobutyl, like this. On the next one, can you guys still see my screen? I go back to my slides here.
Yeah, I can.
Okay, good. Thank you. Okay, the next one, we have the methyl group, and the last one, there's no chiral center. So here's how it goes. If your R group is pointing down, so anything that's going down, so we'll put here R group down, we're going to draw those as dashes. Okay, and if the R group is up, then we're going to draw it as a wedge. So since the alanine is pointing up, the methyl group is pointing up, we're going to draw it as a wedge. And since the isobutyl group is pointing down, I get my pixel eraser over here, we're going to draw it as a dash. Okay, and this is just a convention, like that. There you go. And now we put in our hydrogens, and that's it. Okay, and that is true for any amino acid. If the residue is pointing down, it's drawn as a dash. And if the residue, the R group, I should say, is pointing up, it's a wedge 100% of the time. All right, there you go. And that would be the structure of, that is our leucine. Oops, leucine. And then what do we have next? We have alanine. And then last we have glycine, just like that. Give me a thumbs up on that if you're like, yeah, I think I could do that. I just need to try it myself. Double check it. And I guarantee you that I ask you to do some problems from the textbook. All right, there you go. So I'm going to erase the top one quickly, and I want to show you one more quick thing. Okay. There we go. So I'm going to delete all that. So look, if you were to start with the nitrogen like this, I'll use the blue pen. Okay. If you went up instead of down, right? You see my first bond, I go down. If you went up and then NC carbonyl, NC carbonyl, NC carbonyl, like this. If you did this, there's nothing wrong with it. Okay, there's nothing wrong with this at all. All you'd have to do is, since now the methyl group is pointing down, you would draw on a dash. And since the isobutyl group is pointing up, you draw it on a wedge. Okay, so what I have drawn in black and what I have drawn in blue, those are identical. They're the exact same thing. In fact, if you were imagine grabbing this whole molecule and then flipping it and superimposing it on the top, you'd end up with the exact same thing. All right, there we go. So a little aside for you there. Let's move on and take a look at this one here. Now this one you would have to use a handout, or you'd have to have the list of the abbreviations of amino acids. Just let me double check something here on my computer. Give me 2 shakes of a lamb's tail here. Here you go. So in the chat, I just posted a list of amino acids directly from our textbook. So I just posted it as a PDF because, again, I don't expect you to memorize all the amino acids. It's handy if you do, and I can tell you a funny story about this. A number of years ago, I told my students in 3111 that I was going to give them a bonus question. I was going to collect their quizzes. Then I would hand out a bonus question where they just had to write out all the naturally occurring amino acids. So I collected all the quizzes and I said, okay, I'm going to hand you all a blank sheet and you just have to write down the structures of the 20 amino acids and give me their names. And I went to hand out the sheets of paper and most students were like, you know what, Mr. Dean, you just keep your piece of paper because I didn't memorize them. Anyhow, let's take a look here. We have a pentapeptide here. So look, we have NCC right there. Then we have NCC there. Then we have NCC. I kind of got to go around for this one here. Then we have NCC there. And then the last one, go back to blue, I guess. Then we have NCC here. So again, I wouldn't expect you to have all these memorized, But we did see the first one already today. This is leucine, so leucine, because we have an isobutyl group. Then when we have a methyl group, this is called alanine. So alanine. The next one is phenylalanine because we have a phenyl directly attached to a methyl. So this is phenylalanine, phenylalanine. The next one is cysteine. So cysteine, I'll write this one in black. So cysteine. And the last one is aspartic acid. So we have aspartic. And that's just using the handout if you don't have them memorized. So what are the three-letter abbreviations? Well, let's write it out. We have LEUALAPHECYS, and then we have ASP. That's the five-letter or the three-letter abbreviation rather. So we get that one done. Next, it asks us to come up with the one-letter abbreviations. So it's L, A, phenylalanine is F, cysteine is C, and aspartic acid is tricky. It's a D. Okay, so L, A, F, C, D. And again, they have to be put together in that specific order in order to draw that pentapeptide. All right, so there we go. So if you, again, look at the structure, you see that any R group that's pointing up is on a wedge. Check it out. I'll use the yellow highlighter to double check, but you see that anything that's pointing up is on a wedge, and anything that's pointing down is on a dash. All right. You know, something interesting about the stereochemical configuration of the 20 naturally occurring amino acids is that if you take an amino acid, like the way they're drawn in our textbook, if you haul up that PDF, and I don't have it open, but I can open it quickly here on my computer. If you look at that PDF, come on, open up. There we go. So I'm just going to zoom in on it here, and I'm just looking at it my own dang self right now. He draws all the amino acids the same way. Say, for example, he draws alanine. He makes sure, let me zoom in here. He makes sure to draw the amine on a wedge going down, and then he draws them up like this. Again, this, what I'm talking about right now, has nothing to do with the way you draw this. This is just what you see in that table. If you were to assign the stereochemical configuration, you have the nitrogen as being number 1, right? The hydrogen going in the back is going to be number 4, right? This is number 2, and this is number 3. So we're going back this way, okay, which is counterclockwise. And so the stereochemical configuration of all but one of the naturally occurring amino acids is S, right? This is S. Did anybody try the homework and identify which amino acid is not S? There's only one that's R. Could anybody tell me which one it is? There's only one naturally occurring amino acid that's R. And you could probably look at their structures pretty quickly and figure out which one it is. Sorry, I got to go back to my chat here. Did anybody figure that one out? Okay. The only one that's R is cysteine. Okay. And let me show you why. So if you draw the structure of cysteine, so this again was, this was alanine. Okay. But if we draw cysteine, it looks like this. We have our amine like this. Okay. It's because you have a sulfur here next on this methylene, right? The nitrogen is going to be highest priority. The hydrogen is obviously lowest priority, but now between all these, the carbonyl, or sorry, the carboxyl is always number 2 in every other amino acid, okay? Because it's this carbon is attached to oxygen, oxygen, oxygen. It always wins, except for in this case, where it's attached to sulfur, hydrogen, hydrogen. Well, sulfur has a higher atomic number than oxygen, and so this is number 2, and this is number 3. So you go like this, which is clockwise, and so the stereochemical configuration of cysteine is R. It's the only one that has the R configuration. You don't believe me? You can go through the list and prove it to yourself, but it's the only one that has the R configuration. All right. Give me a thumbs up if you follow me on the Kohn-Ingold pre-log rules or the stereochemical configurations of amino acids and how to draw the residues correctly. Great. Wonderful. Again, I've assigned some more practice problems from the textbook. You want to be sure to take a look at those. Okay, give them the old college try before quiz 25. But let's move on to the next section, which deals with sequencing a peptide, right? Peptides are big molecules. So let's say you have 40 different amino acid residues all linked together. Okay, how do you determine the order of that? What do you do? I mean, taking an NMR, whew, that's going to be busy, right? You're going to have a lot of overlapping signals, so that would be tough. Mass spec, whoa, you just have a really high molar mass, so that's going to be difficult. And so there have been ways developed in order to identify or elucidate the sequence in which the amino acids are linked together in a peptide. And one of those ways is to use what's called the Edmond degradation. So Edmond degradation, which was obviously developed by somebody named Edmond. And the way that it works is that it says you remove an amino acid from the N terminus of a peptide. Remember, I told you that you go from the N terminus, which is on the left-hand side, and you go all the way over to the C terminus, which is on the right-hand side. So you're taking the N terminus, so you're removing something from the left-hand side, so to speak, of the peptide, and you convert it into a phenylthiohydantoin, or a PTH derivative. Okay, and then what you would do is you would analyze that PTH, or that phenylthiohydantoin derivative, maybe by mass spec, in order to identify the amino acid. So check it out. Here's a big old peptide, right? In this picture, all they're doing is zooming in on the N terminus, right? So they've kind of got it spun around, right? Now they're going from the N terminus, right? And then the C terminus is over here. And I know that's not the convention. Normally we put the N terminus on the left. This is just done for instructional purposes to show you, wow, this is where the reaction occurs. Okay? So what you do is you react the N terminus with this sassy little molecule here, which is called phenyl isothiocyanate. So you take it and you react it with phenyl isothiocyanate, okay, in the first step. Then you treat it with TFA in the second step. So this is trifluoroacetic acid, which we might have looked at for a split second earlier on in the class. So you do these two steps. So phenyl isothiocyanate followed by trifluoroacetic acid, and you make the phenylthiohydantoin derivative. You remove this part from the peptide, so you're left over with a new N terminus to do a second degradation. But the idea is that the phenylthiohydantoin derivative, all of this stuff is going to remain pretty much constant, okay? But the R group is going to change, isn't it? Right? If it's an alanine, it would be a methyl. If it's a leucine, it would be an isobutyl, so on and so forth. And so you can analyze that by mass spec to determine the identity of the amino acid at the N terminus, and then you just keep doing it over and over and over, right? Then you determine the identity of this one. So this process can actually be automated. So there's actually instruments. I was going to say machines, but technically it's an instrument that can do this and keep going all the way up to 50 different amino acids. So kind of cool when you think about it. Something that I've never done in my life, but I know it's a way to determine the or elucidate the structure of a peptide. Now the whole conversion to the phenylthiohydantoin, I will never ask you this mechanism. It's just shown here. I'm going to leave it as an FYI thing for you if you want to take a look at it. But again, I've never asked a student a question with the mechanism of the phenylthiohydantoin formation. Not nearly as important as something like saponification, right? Not even in the same realm of importance in this class. All right. So that was one way. So that covers the Edmond degradation, right? So the Edmond degradation involves forming that phenylthiohydantoin derivative and then analyzing it, and then you just keep going. You keep picking piece after piece after piece off until you've determined the structure of the entire peptide. Another way, and if you've studied biology, you've probably heard of enzymes like trypsin and chymotrypsin and elastase, things like that. Well, another way to do it is to use enzymes to break up the peptide into smaller peptides, and then we can analyze all the different fragments after the enzymatic cleavage, and we can kind of piece it together to determine the structure. A couple of examples of enzymes that are useful for sequencing peptides. The first one is trypsin, right? I just mentioned it. The trypsin cleaves the peptide bond on the C terminus of arginine and lysine. Now, what do you notice about arginine and lysine? They're both basic amino acids, aren't they? They're both amino acids that have basic side chains, right? They both have basic side chains, all right? So what happens is trypsin, and this isn't covered in our textbook whatsoever, but kind of like, where's my pen? At the bottom of the pocket of trypsin, which again is just an enzyme, there's an aspartic acid or a glutamic acid. I don't remember exactly which one it is, but it's at the bottom of a pocket. So you have that negatively charged carboxylate, and it attracts, the basic portion, and just through electrostatic interactions. Anyhow, and then it gets cleaved. It's a type of protease. It's called a serine protease. You'll learn about that in biochemistry. It's neither here nor there. So what if you're like, oh, Mr. Dion, you're losing me. What's important about this, right? Tell me what I need to know. Well, let's say you had this peptide right here, right? You've got, what do you see? 9, 10, 11. You got 12 amino acid residues in this peptide. Well, if you were to treat this with trypsin, what it does is it cleaves the peptide bond on the C terminus of arginine and lysine. So we have a lysine here and we have an arginine here. So it's going to cleave the peptide bond on the C terminus side. Well, we know it goes son of a gun, it goes NC carbonyl, our amino acid, doesn't it? Right? So that means that you go NCC, so it's going to be on the right-hand side of the lysine, so to speak. So you're going to break it there, and then you're going to break it here as well, and then you end up with these 3 fragments here. And you're like, okay, whoop-de-doo. Well, the first thing that you'll notice is if, let's say you had no idea what the structure of this peptide was, if you treated it with trypsin, and you know what trypsin does, if you got these fragments, well, you see that this one ends with a lysine, this one ends with an arginine, but the other one ends with a histidine, right? So that tells you that since that one didn't get cleaved, that must be your C terminus, right? This must be your C terminus, and then C terminus, and then you can work backwards from there. All right, but that still isn't enough information, is it, right? We would need more. Well, we could take the same peptide, so here it is again, and now we're going to treat it with chymotrypsin. And chymotrypsin is going to break the peptide bonds on the carboxyl end of aromatic amino acids, phenylalanine, tyrosine, and tryptophan. So again, we take that same peptide that was broken here and here the last time, but now we take it and we get a bunch of new fragments, right? Because we break it on the C terminus, or the carbonyl side of phenylalanine, tyrosine, and tryptophan. So this time we get 4 fragments. You see that these 3 all end with those 3 amino acids of interest, but the last one ends with histidine. So again, that must be our C terminus. So what we would do is we would take this information, these fragments, we would analyze them at the same time as these fragments, and we would put it all together, and we would be able to elucidate the total structure of the 12, or elucidate the sequence of the 12 amino acid residues in this peptide. All right, so with all that in mind, let's try a question that says a peptide with 22 amino acid residues is treated with trypsin to give 4 fragments, and it's treated with chymotrypsin to yield 6 fragments. Identify the sequence of 22 amino acid residues in the starting peptide. Well, we know that trypsin is going to cleave them on the carbonyl side. So let's write it up here. So trypsin will cleave on the carbonyl side of arginine and lysine. So look, if we look at the trypsin fragments, we have arginine, lysine, arginine. We've got a valine over here. So that suggests that this is my C terminus. Okay, let's do the same thing with the next one for chymotrypsin. So chymotrypsin. Okay, that's going to cleave on the carbonyl side of phenylalanine. Okay, what else? Tyrosine and tryptophan. So tyrosine and tryptophan. So if we look over here, let's see, we got tryptophan, tyrosine, phenylalanine. Oh, we've got a valine. Okay, so again, this suggests that this is the C terminus. Okay, so we know what the C terminus is. Okay, and we know that the valine on the C terminus is directly attached to an alanine, isn't it? All right, so we can cross these 2 out, these 2 here, and we're going to start with our C terminus. So I'm going to start in the bottom here. So let's do it. Let's go valine. And then again, that's our C-terminus. That's going to be attached to an alanine. Okay. Well, this again is our C-terminus. So then we must have phenylalanine, proline, glycine. So let's throw that down. Phenylalanine, proline, glycine. Okay. So now what I'm going to do is I'm going to go over here. Look at my chymotrypsin fragments, and I'm going to try to find glycine, proline, phenylalanine. And I do right here. I have glycine, proline, phenylalanine, the three that I just crossed off. And what are the three that I have before that? I have arginine, cysteine, and methionine. So we'll cross those three off. Then I look for methionine and cysteine over here. I find them right here, as well as that arginine. So I have methionine, cysteine. Then I have these three, phenylalanine, histidine, and I'm going to go back up here. And then tryptophan. So I'll cross those off. Well, I see that this is the only tryptophan in the entire thing over here in the chymotrypsin fragments, the one that I have highlighted. So, yeah, and I got rid of this one, the phenylalanine and the histidine. I also got rid of, yeah, I think that's it right now. Sorry, I'm just double checking myself here. So valine, phenylalanine, proline, glycine, arginine, cysteine, methionine, phenylalanine, histidine, tryptophan. And then I'm going to have all these ones here. So one's up here. So then I've got arginine, leucine, isoleucine, valine, proline, glycine. So I can cross all of these ones off right here. Then the lysine, the only lysine that I see over here on this side is this one right here. I'll highlight it in green. This one right here. So that means before the lysine, I must have the tyrosine. So I'll go back here. So I've got the tyrosine, alanine, the valine, and the methionine. Okay, oops. Can do better than that. The methionine. So that eliminates all of those. It eliminates these. There we go. And the arginine, the valine, I already got rid of that. The second valine. So all of this here is this one right here. Okay. So I got rid of that too. So that's everything. If you count it up, I have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Oh, fiddlesticks. Must have skipped one somewhere. Oh, yeah, I skipped the phenylalanine, didn't I? Yes, I skipped this one right here. So nobody stopped me. So I'll just get my eraser here. So this should be a phenylalanine. There we go. And then we should have a methionine over here. So there you go. There's my 22 amino acid residues. And again, it's like solving a puzzle. It's just like a puzzle. All I did was I took the fragments from trypsin and the fragments from chymotrypsin, and then I just, pieced them together until I used up all 22. And there you go. All right. So that's how you sequence a peptide. And there we go.